Now that we know how to quantify forces in 2D, it's time to have a look at the equations that must be used to determine these forces, Newton's laws of motion. Let's start with the first law. Listen carefully. An object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. An object at rest stays at rest. This is equilibrium. This is statics. So here we are talking about statics. Unless acted upon by an unbalanced force. What's an unbalanced force? Let's consider an object on which multiple forces act. All the forces together should keep the object in equilibrium. Hence, we look at the sum of forces, which we write as the sum. So this is the sign for sum of the forces. We can indicate that forces are vectors with an arrow on top of the F. When are these forces in equilibrium? When the sum of forces is equal to 0, the forces are balanced. So this is equal to 0. This is the main equation of statics. As forces are vectors, the sum of forces must also be 0 in all directions. That is, we can indicate that this is a 0 vector with an arrow on top of the 0. In the next video, I will explain how to use this equation for calculating equilibrium forces for a particle in a two-dimensional coordinate system. Now, let's have a look at the second law. The acceleration of an object is proportional to the net force acting on it, and its direction is aligned with the direction of this net force. So, what do we read here? What it says is that the force acting on an object, so the net force, the sum of all forces acting on the object, has the same orientation as the acceleration on the object. And it is proportional to the mass, so it's mass times acceleration, and acceleration is also a vector, which means that the direction of the sum of forces will have the same direction as the acceleration. So what we're talking about here is about moving systems where there is a change in the motion. So this is dynamics. And this will be covered in different courses. So finally, let's have a look at the third law. The action and reaction forces between two contacting bodies are equal in size, opposite in direction, and collinear. What does this mean? Let's consider the case of a large weight which is placed on a table. We will look at the combination of weight and table, as well as at the table and the weight separately. I will draw them first. So let's say we have a table. And on top of the table we have a weight of 100 kilograms. And let's have a look at the weight and the table separately as well. So let's consider the forces on the complete system at first. the weight is much heavier than the table, so we will neglect the weight of the table. And we have a gravitational force acting on the weight. There's also a force on the legs of the table, which keeps the whole system in equilibrium. So each leg has a force which is acting in upward direction. And then these forces will be acting on the subsystems as well. So we can copy these forces to our subsystems. If we now look at the mass or at the table only, we can see that they are not in equilibrium. With these forces, the mass would be accelerated downwards and the table upwards. However, there's a contact force between the mass and the table that prevents both from accelerating. The mass acts with a downward force on the table. And the table acts with an upward force on the mass. This is exactly what the third law of motion states. When one object acts with a force on another object, the second object will act with the same force on the first object, being of exactly the same size but in opposite direction. That is, action is minus reaction. This is a key equation in statics. We will need the principle of action is minus reaction to calculate forces in systems that are in equilibrium. So in this case, the size of both of these vectors is exactly the same. So this vector and this vector have a certain length. Let's call it Fc for the contact force. And the length of these vectors, so the size of the force, is exactly the same. The only difference is that for both subsystems, the forces are acting in exactly opposite direction. By discussing Newton's laws of motion, we have now gained understanding about the basic concepts of statics. We will now use the first and third law to start writing equilibrium equations of systems.